Hello and welcome everyone to my first presentation on quantum computing, simulation of molecular energies. Have you ever heard of quantum computing? Why is it such an important research field? Why do we need quantum computing? Is this new technology useful? Let's begin with a definition. Quantum computing is computing using quantum mechanical phenomena, such as superposition and entanglement. It combines the knowledge of both quantum physics and computer science to create a large-scale quantum computer which would be able to solve certain problems much more quickly than any classical computers. How can it do that? A quantum computer is a system that performs quantum computing. They are different from binary digital electronic computers based on transistors. Whereas common digital computing requires that the data be encoded into binary digits, bits, each of which is always in one of two definite states, 0 or 1, quantum computation uses quantum bits, or often called qubits. Qubits exist in a state of superposition, which means they can be in two states at once, rather than being restricted to a single binary state. With this quantum physics mechanic, these computers are able to efficiently solve problems which are not practically feasible on classical computers. Currently, the development of actual quantum computers is still very costly and technically challenging. However, many organizations are investing in quantum computing research in additional effort to develop quantum computers for civilian, business, trade, environmental and national security purposes. Meanwhile, both practical and theoretical research continues, and experiments have been carried out in which quantum computational operations are executed on classical computers with a very small number of quantum bits. In our first experiment, we will take a deeper look at how quantum computing can help with other scientific fields, particularly chemistry. Quantum simulation of molecular energies allows numerically accurate prediction of chemical reaction rates, promises significant advances in human knowledge of chemistry and could enable the design of new catalysts, pharmaceuticals and materials. Physicists have been able to develop quantum algorithms to estimate the molecular energies, such as the phase estimation algorithm and variational quantum eigensolver. The figures show the relationship between bond length and energy. The red line is the exact value while the dots are estimated by the quantum algorithms. This result shows that quantum computers are able to estimate the molecular energies with high accuracy. This would be a strong evidence of the power of quantum computer and its application. Next, we will attempt to perform this experiment using quantum computing on a classical computer. This demonstration uses Microsoft's Quantum Development Kit for Hamiltonian simulation by showing how to simulate molecular hydrogen. We particularly use the phase estimation algorithm in this code. The chart illustrates the correlation between bond length and energy of hydrogen, with step of 0.05 on x-axis. The simulation shows that quantum computing can achieve quite accurate estimations, even without a real quantum computer. This result motivates more research in quantum computing and more application development for many other fields. Thank you so much for your attention during this presentation. We do hope to see more application of quantum computing in the near future. Feel free to contact me if you have any inquiry.